Good afternoon, everyone, and welcome to the VeriSign Labs Distinguished Speaker Series. My name is Bert Kaliski. I'm the Chief Technology Officer at VeriSign, and we're so pleased to have you here with us today. This is the first time we've had one of our Distinguished Speaker Series outside the United States, outside our headquarters, and to have it here in Fribourg in Switzerland is just a delightful indication of our commitment to the best operations and the best talent all over the world. We're grateful for the presence that we have here. You may know the VeriSign brand. You may know many of the services that are powered by VeriSign. You may interact with them every day, and hopefully you don't even notice it because they work so well, you can take them for granted. At VeriSign, we operate some of the largest name servers for domain names in the internet. We operate 2 of the root servers of the internet. These are the servers that are continuously running so that you can look up resources on the internet, on the web, do email, do e-commerce, and so on, and it just works. We were founded in 1995. We have grown to be a company with over 1,000 employees, around $1 billion US of revenue, and we have services both for domain names and for enterprises, specializing in registries and in certain security protections. And as you'll see, research in these areas really makes a difference for us. Our mission, as stated by our Chief Executive Officer, Jim Bidzos, is to enable the world to connect online with reliability and confidence. And you'll see how we can achieve that more effectively today. We have a statement that powered by VeriSign means a number of things, and I won't read all of them to you here. You can find them in our other literature. But it's important to us that we get things working right so that they accomplish others to meet their objectives that depend on this confident navigation. And to do that, we operate servers all over the world. This is a diagram, a map of the locations of more than 70 of our servers that provide domain name resolution in all geographies, so that any system, any application, any device that needs to look up a domain name can find a server nearby and find an answer, as well as other services that we operate. Fribourg is an important part of this constellation of services because it has one of our major data centers, providing us with the assurance that we always have capacity to be able to manage the transactions across our naming business. We look in a number of areas of investment and innovations from the DNS ecosystem around through cloud computing and other areas of security, because we want to be sure we have the best practices and understand how those practices are impacting the world. And so to do that, one commitment we've made is to invest in research. We have a program called VeriSign Labs, and VeriSign Labs follows a model that's an enhancement of what you may have heard in recent discussions, the model called DevOps. DevOps brings development and operations closer together for a more rapid process of moving ideas into practice. We take that a step further and we call it R&D ops. Our researchers and our developers and our operators work as a team for this interaction and feedback that ensures that not only new ideas, but the foundations behind them are considered when we're putting something into practice, and vice versa, to enable our researchers, collaborators in universities and elsewhere, to have more of the context, which often means more of the data, to understand what problems need to be solved. As part of VeriSign Labs, we have a Distinguished Speaker Series. And as I mentioned, this is the first time we have held a Distinguished Speaker Series event outside of the US, a perfect place to do it because of all the benefits that we have with our own R&D center based here in Fribourg, with the talent, with the emphasis on academic excellence, the universities all around us, and the pleasure to have two of our university collaborators here presenting their research to us today. So I'll stop my remarks so that they can share some of theirs. Our first speaker today is Professor Jean Henebert, who is from the University of Applied Science here in Fribourg. And he's had some industry experience and a solid academic background, working in industry in the United States in communications and also working at UBS, and previously receiving his PhD in speech and speaker recognition here in Switzerland at EPFL. And he's working now on complex systems at the EcoSys at the University of Applied Sciences. He will talk about phonetic research applied to internet and domain names. People start with some spoken understanding of what they're looking for. How do you make a name that makes sense to them so they can navigate confidently? So, Professor Henebert.
Thank you, Bert, for this introduction and for the opportunity to present our research, and in partnership with VeriSign, we will present today what we do in phonetic domain name research. Let me start with a nice picture of Fribourg. This is our city. And as you can see, we have a wonderful new bridge that we will be able to use in some months now. It's going to be open. And as you can see, Switzerland is a very nice country, right? And Fribourg is really at the middle of Switzerland. It's at the intersection of linguistic regions. At the left side of this bridge starts the German-speaking region. That extends to the rest of Switzerland in the German part, and then Austria, and then Germany with about 80 million people speaking German. On the right side, you have French-speaking region, going to Lausanne, Geneva, and then France, a part of Belgium, where I'm coming from. And then it's also about 80 million people. And then if you go across the mountain, about 100 kilometers, not so far, start the Italian region with about 60 million people speaking another language. And in Fribourg, we have this chance to be at the intersection of all these regions. And then it makes sense for us to play with languages because we like it, and it's our daily life, right? So let me start with my talk. It's going to be about international domain phonetics. So it's a project that is done in close collaboration with VeriSign. This is the team members over there. I'm the first one by alphabetical order, but I give all the credits to the other one that have been bringing all the ideas and the work, actually. I'm just entertaining you today. So let me start with a little movie, and I will ask you to pay attention to what this wonderful lady is going to be telling you. It's a YouTube movie. You can find it on YouTube. Just pay attention to what she's saying, right?
Bonsoir. Chaque heure le boulet son sa voix de 4 dents. Che le buono oiseau gioschi monard, je le podimo. Mangiorno, pratti, solla viretto, putta pesca, madra solla. Português que forma choice redetsaio al merianto. Gramada hauda faduro, ki sanchere u padresa me. I'd say I kill it in my bones. Dumb things in it. It's like a miraculously mobilizing felt tip pen, like a ordinary sentence of a marinating follow. Chimisi nada turu yukimas. Yukitura basanchito yuski di matoska. Masakituro yukimikte. La maniera casual mató da mierda, que tondo quise el solo un lugar abierta per viva con todo cómico pueses. A huevo, cabrón. Yeah, I mean, Trevor Mazendry appearing like Monin Fair. Follow me, like a pending French racket, Bologna value precisely. Hello? Dapat dima. Pedep milkar babaji pani midega adiyamal magar jaunga. Vidigata miligi mi bariba. مقلوص الواحد على الحباب ما يعرق التهدي من أصل يشتقت لي عرهم القلاص أنا أدرس اللغة العربية في البيت.
So, maybe you speak some of the languages that have been presented. Did you understand what this lady said? No, right? But still, it sounds like the language, is it? How does she make it? Do you have an idea? Is she using random sequences of phonemes? Yeah, maybe in the target language, but actually it's not really random, right? It has some structure, right? If she would be taking random sequence of phonemes, it would sound quite strange, but in machine learning, we say she's using patterns of sequences of phonemes. And this is exactly what we are going to exploit. If we can find nice technologies to spot these patterns, maybe we will be able to play with it to build product or nice business cases. Let me convince you that these patterns do exist. This is a kind of file we play with in this project. It's called dictionary files. So on the left side, you see words, okay? And on the right side, you see sequences of symbols that represent the phonemes, the sounds that correspond to the word that are on the left part. And as you can see, the file is pretty big, right? It has a lot of input, a lot of data in it. Let's have a look. It's a US English dictionary file, so it's about 200,000 names, common names, a bit of family names, and so on, but not all names. This is a problem for us, as you will see. And then let's try to find these patterns, right? Let's take, for example, a sign, like in VeriSign, okay? And then sign appears in a lot of words, as you can see. Web designer, 99 design, and so on. And then if we look at sign, we can spot on the right side that you have a sequence of phoneme that correspond to this little part of word, as we say, okay? D, A, big I, N, these are symbols representing phonetic sound in International Phonetic Alphabet. And let's find another pattern. And I'm looking in this file, and you see we find this pattern, resigning, resign, and so on, unresign, resignedness. And this pattern comes again and again and again. So if we could build, and this is actually what we did, if we built a technology to spot these patterns and to play with it to do things, okay? So we have two questions, one which is scientific, one which is business. From a scientific point of view, can we automatically discover such phonetic structures? The answer is yes. And the second question, can we use this information to enhance web experience? And this is very interesting in some domains, like, for example, domain name suggestions. So let's imagine we have this technology. So I'm willing to book or to buy a domain name Airmix, airmix.com. Of course, airmix.com is already taken because it's a bit busy. And then the system will be able to automatically suggest closely sounding domain name. So if I'm looking for Airmix, maybe the system will propose Airmix with a R and mix, Airmix with a CS at the end, Airnix, which is closely related phonetically, and so on. So there is a clear interest in this to suggest in a new way domain names for web users. So the question from a scientific point of view, I'm not going to be very technical, but I will give you a hint on how we do this. We have different challenges. The first one is to transform any input into sequence of phoneme, even family name, even company names, even names you invent. So these inputs we don't find in our dictionary. So we need to generalize. That's the first challenge. Then we need to spot the phonetic patterns, as I have shown you just before. And then we need to replace the patterns with similar sounding ones. And then we need to go back into the graphemic world to translate back into a sequence of characters. Okay, so we came with this processing chain that I will show you in a few minutes. But VeriSign came with other constraints, like we need to scale to as many languages as possible. So if we find a good technology for French and it takes 6 more months to build it for German, then it's not very useful. So we need to scale to as many languages as possible, and we need to be efficient as well because we target to have a real use of what we do. So this is a processing chain. We have actually 3 parts. I'm just going to give you a little bit of hints about how it's working on the first part. So we have a G2P grapheme to phoneme mapper that will map any word into a sequence of phoneme. Then we have a P2P phoneme to phoneme mapper that will bring some alterations. And then we have a P2G to go back to graphemic representations. So let me just focus on the first building block so you understand a bit how we do it. We actually build index of correspondence between grapheme and phonemes looking at the context of the grapheme. So For example, if I take the letter I, isolated, I will be mapped to phoneme E, like in pixel. But E is not good for air mix, as you can hear it, right? So we need to look a little bit more of context. So let's take a letter on the left. AI is still not good for air mix, but it's mapped to, in some other words, to I, like in gain or vein, okay? The right context for us is 3 letters. So there we know that air is mapped to a special phoneme that is written with a little star, which means R. Okay, R mix, like in R mix. So the technology we built is able to look at the context of a single character, looking left, right, left, right, left, right, building context, enlarging context, until we find the right correspondence in the phonetic domain. And then we store this correspondence in an efficient way, in an efficient data structure, using trees. Why trees? Because lookup in trees are very efficient, right? We can build very fast technology in terms of algorithmics. So I'm not going into details, but we build a tree. At the top of the tree, we have the basic correspondence between grapheme and phoneme. The downer in the tree, the more specific we are, the more exceptional we are in the way we pronounce sound. So we go in the tree looking left context, right context, left context, and so on. So for example, you have the I of air mix, we look at the M and the I, and so on. And then at the bottom of the tree, we find the right correspondence. We have a pre-processing step. I'm not going into detail, but we use other kind of algorithms. It's quite complex at some point. We need a pre-processing step to align the grapheme string and the phonetic sequence in the right manner. So this is the output of this pre-processing step. We use hidden Markov models, kind of complex statistical model to do this, but we could make it. And then we are then able to build the tree that I just presented before. So the central idea of the technology we have put together in this project is to solve the mapping problem between grapheme and phoneme and the indexing problem using a very efficient tree-based lookup. And then I'm not going to explain P2P and P2G because it's a kind of similar way of doing things. It's a reverse problem for the P2G. And actually, the P2P comes as a byproduct of the lookup. And we exploit the structure of the tree to find alteration of the phonetic correspondence. So what can we do else? So you know now that we can do similar sounding domain name suggestion. That's one business case. Another business case could be brand protection. So let's assume I'm the owner of perfume.com, for example. The system is able to suggest a similar sounding domain name, so we can protect our brand, which is a very important matter for companies. And we could, for example, registering similar sounding domains to cover a potential phonetic misspelling and so on. Something else we can do with the technology is to mix languages. For example, if we use the dictionary of German speaking for the first part and English speaking for the last part, we can answer questions like this one. We can mix language. For example, I'm speaking about Der Spiegel, which is a famous magazine in Deutschland, in Germany. And then an English-speaking person is listening to me. And how would he write it phonetically? This is the question. By mixing languages like this in our processing chain, we can answer questions like this. So I am German. I would like to know what are the potential phonetic spelling of my domain by native or non-native users so that I can, again, do brand coverage, but in an international perspective, if you want. Okay? And I can catch up maybe important part of network traffic doing this. Next business case is what we call Latinization of names. So, for example, people in Russia, they use Cyrillic characters, and maybe for international reason or for other reason, they would like to have a kind of transliteration of their representation into the characters of another language, like, for example, Latin character here. And then the technology is also able to do this. So it's kind of also important use case of the technology. Yeah, to come back to our nice lady, right? We could also simply browse in the tree, generating jumps randomly, respecting the probabilities of going left or right in the tree, and so on, and then generate potentially good sounding domain names. So we constrain, for example, a length of 6 characters, or 7, or 8, whatever, and then the system is able to generate thousands and thousands and thousands of potentially good sounding domain names. So this is an output of the system with a length of 6. As you can see, it's sounding quite okay, right? It sounds like English words, isn't it? Well, maybe not all.
Well, Google didn't exist. That was great.
Yeah, exactly. Yeah. So Google is a good example. I will show you some example with the name Google just after. So the technology we built together with VeriSign is ported on different languages. We cover now English, French, German, Spanish, Portuguese, Italian, Russian. And then we are hitting a bit of more difficult languages for different reasons. Turkish, Korean, Japanese, Hindi, Arabic, and Chinese are under work. Some language we know already we will have a lot of difficulties. Some other languages that are in the list we will probably find solutions. They are just more difficult because, for example, Chinese is a tonal language, and they have an ideogram representation of the string, which makes our technology is not scalable to this kind of representation. Arabic is a bit strange as well because they don't pronounce vowels. They don't write it. They pronounce it. They don't write it. So in the grapheme representation, we don't have the vowels, which makes it difficult for our technology. We need a pre-processing step to handle this, and so on. So I'm at the end of my presentation. So I'm playing a bit with the technology to write you this slide. The project is supported by the Commission for Technology and Innovation. So the CTI, which is almost fully funding the academic part of this project. And of course, we have the support of VeriSign internally for building this very nice project. So while you will maybe ask me some question, I will play the little demonstration of our tool. Yeah, I just need to launch the... maybe we can watch together the first few examples. So basically, we have the phonetizer part, the graphetizer part, which are the two blocks where we can choose the languages. We choose a target language for the phonetizer, target language for the graphetizer. We input a grapheme. We have some options, but we just use the standard thing. You see the computation is very fast. It's less than 2 milliseconds. To get the answer. The trees are really efficient. And then you see I have put VeriSign. You have some suggestions, alternate suggestion for VeriSign. I think it sounds good, right? It's quite close. Let's try with Fribourg. Okay. So Fribourg. Fribourg. It sounds if I would build an alternate site about underground Fribourg, I would maybe look at this pronunciation. That would be nice. And then, yeah, let's try with famous Google. Let's see what we get. Of course, you can do brand protection targeted on specific sequence of phonemes. So I just click on the first line to get specific on a sequence of phoneme. And this is what we get. We get the first one, which is a good sign that we find back the right pronunciation, so the system regenerate the initial input. But then we have a very nice, I think, suggestion for in a brand protection case. And then we can mix languages, as I said, with Spiegel. Just give you another example. So we have German speaking and target in US English. And then Spiegel, as we hear the sh of the German-speaking guy in the grapheme suggestion. So,
Thank you very much.
thank you.
Thank you. That was very well done, and that is about where good domain names come from, among other things. Well, what happens when you start having transactions with domain names and other things? We get into the world of big data, and our next speaker is Professor Philippe Coudray-Moreau from the University of Fribourg. He also received his PhD studying in databases from EPFL, and then has industry experience working for HP, for IBM Research, for Microsoft Research Asia, and is the director of the Exascale Info Lab. So this talk will be about big data and its several applications.
So today I'm going to tell you a bit about big data, which is my favorite topic, of course, and I'm going to tell you a bit about some projects we did in collaboration with VeriSign. Just a little introduction. So I'm a new prof at the University of Fribourg. We are in Pérol 90, just in front of the École d'Ingénieurs, so we have very nice neighbors and good collaborations too in this Pérol plateau. I have a kind of a special lab more focused on research rather than teaching, right, and financed mostly by the Swiss National Science Foundation, by some companies, thanks a lot VeriSign, and by some private foundations, and as I will tell you a bit about today, I'm mostly interested in data and, big volumes of data. So on the menu today, I will give you a bit of the buzz about big data. I guess you all heard about big data. It's big even in Switzerland, right? We're always a bit behind in terms of buzz and potentially new marketing in terms of IT. And then I will tell you about those 3 projects. So just such that I have an idea of the audience, could you just raise a bit your hand if you've heard about big data? 70, 80%. And could you raise your hand if you know what HDFS is? 50%. Okay, so that's what a bit I thought. So I will start with a bit of the buzz, right? And a bit of what is big data, what are we doing, why is it important, and why is everyone talking about it, actually, right? So I'll spend a few minutes on that. The idea is basically that today we have, can I have a pointer? Yeah. We have new data formats, right? I'm coming from a database background, and databases for like 2 decades, they were about those tables. You've all seen, I guess, those database tables, right? We call them relations. And databases were all about relations and tuples, which have different columns. And today, this is not true at all anymore in the sense that we have tons of new data, multimedia, array data like vectors, multidimensional data. Text data is extremely important for companies today. Social data, right? We have Facebook, etc. Web data, simply. We want to put data on the web, which is usually non-relational, right? It's not your grandfather database. We have new machines. And as you know now, it's all about SSDs, main memory systems, multi-core systems. We have extremely big data sets, what we call peta exascale data sets, right? Data sets with lots of zeros in terms of amount of data. And in the end, we have a big obsolescence of traditional information infrastructures, right? I don't know if you've heard about it, but if you're in the IT world, you definitely heard about it. Basically, the old database systems that we were using for about 2 or 3 decades, right? I will not name products, but you all know some of those databases. They were invented 40 years ago, right? They were coded 35 years ago. And the environment was totally different. So today we have this paradigm shift where basically those dinosaur database systems that have been used for decades, they cannot actually tackle the problems we want to tackle in terms of those big data and how to use the data. And everyone is talking about it. Nature, right? It's the top scientific journal for biologists and all those guys. The Economist, Wired, they had this provocative kind of title a few years ago. The end of science, right? The quest for knowledge used to begin with grand theories. Now it begins with massive amounts of data. It's of course provocative, it's not the exact truth, but it's a trend, right? If you take biology today, if you take medicine, if you take many domains, it's all about data, crunching the data, and get some idea about what you should do, right? It's a data-driven, in the end, methodology. So this is true for science, this is true for web companies, this is true for governments, companies, financial services. It's a big trend. So the idea in the end is that you have tons of data, right? What I usually say is that big data, it's not really a technology, it's a fact. If you are in a big company, if you are in a big school, in a big government, it's a fact, you have big data. And then you can use it, it's an opportunity or not. So if you have a lot of data, if you have the right technology, and that's what we are working on, then the idea is to get actionable insight, right? You want to have some idea from the data, but not some abstract idea. You want to have some idea using which you can make a decision, you can implement a process. And the idea for companies, of course, is to make big bucks out of it, right? To make money, to generate revenue. Of course, if you're a government, the process will be similar, but in the end, you want to have perhaps a better service, right? And in terms of the insights, you can do some traditional reporting, monitoring, but it's mostly about today modelization, right? You want to model the process or the users you have to give them better service, personalized service, and prediction. That's the ultimate goal, right? To be able to see the future. It's impossible. Sometimes you can get close, sometimes not. Everyone is talking about big data, right? Supposedly it's going to create tons of jobs. If I look at the market for my students, I think it's the case, right? It's a very hot market at this point. Lots of revenues. Obama launched a big data initiative a couple of years ago. We're still waiting for the Swiss big data initiative, right? So if you know politicians, tell them that we are a bit behind. We need political support. To come back to Switzerland, that's an interesting article from a couple of years ago from the New York Times. It's about Davos, right? You all know the World Economic Forum, big event in Davos where lots of people, important people are meeting. And it's super interesting that 2 years ago, this World Economic Forum declared data as a new class of economic asset, like currency or gold, right? It's a paradigm shift. It means that previously, you had, as a company, in terms of assets, you had gold, you had perhaps, buildings. Now data is a new asset. If you have data, you should leverage, right, this data, because this is potentially extremely important in terms of the assets you have. Supposedly, it will generate tons of revenues across sectors. We see today, for example, in the healthcare system, in biology, in medicine, this is huge. Of course, public sector, mostly in the US, I would say, at this point. Location data, retail, manufacturing. So it's a kind of a global trend, right? And to come back a bit in terms more of the technology, what you can use today to leverage big data and to have some of this, actionable insight I was talking about. This is one of the recent pictures of what you can do, right? This is a fragmented market. You don't have, as it was the case kind of 10 years ago, you don't have 4 players selling you kind of data software, right? And they were all a bit the same. Today you have a real fragmentation. The problems are so complex from an engineering perspective, but they are so worth it in terms of the money you can make that you have basically one specific solution for every problem you can have. So you can think that this is chaos or that this is sad. I think this is a huge opportunity, right? From an engineering perspective, for new companies, for new business, this is a huge opportunity that typically Switzerland could leverage. Since Switzerland, in terms of our mindset, our kind of companies, we have a lot of data. We know a bit how to deal with the data, so we could do potentially some interesting things using big data. So what is big data in the end, right? I haven't given you a concrete definition. There is no strict scientific definition. Usually what people have been talking about in terms of what is a big data problem is the 3 V's, right? It's Gartner, 2 years ago actually. It's a very recent field, right? So typically, if you're asking, do I have a big data problem in my company? Well, you should look at those 3 V's. You have a big data problem if you have a volume problem, right? If in terms of volume, let's say petabyte, terabyte size of data, you have tons of data. But perhaps you have a smaller database, let's take, for example, a disaster recovery or stock exchange. The amount of data is not big on the stock exchange, right? But the velocity is big, meaning the speed the data is inserted into the system. Typically, in terms of stocks, you have like what, a few megabytes perhaps per day of stocks, but it's continuous, right? And you have to act fast. If there is suddenly a change in the stock, you have to actually do something in like, a few seconds, perhaps a few milliseconds. So you have a velocity problem in that sense. And finally, perhaps the most difficult problem of all those big data aspects is variety. It's basically data integration, which is one of the biggest IT problems today. It was one of the biggest IT problems 20 years ago, and it's going to be one of the biggest IT problems 20 years from now. It's extremely complex, as you know. You hear all the horror stories in Switzerland about, the government trying to do that, to bring systems together, right? You have system A, system B, you want to merge them, you have this variety problem, and then usually you have a catastrophe because it's extremely difficult to have heterogeneous data and to try to bridge them. So that's a bit the idea in terms of big data. I hope I could kind of convince you in 5-7 minutes that it could be potentially interesting. It's a big trend. If you're interested, I can give you a few pointers, both in terms of the research and, of course, the applications, which are phenomenal. For the rest of this talk, I will basically be talking about 3 projects we have in my lab, XI, the Exascale Info Lab, in partnership with VeriSign. And I will talk about 1 volume problem, 1 velocity problem, and 1 variety problem. Like this, I will try to cover a bit the whole spectrum of big data. So I asked you about HDFS before, right? About half of you guys know what is HDFS. HDFS is basically the file system of big data, right? It's the file system of Hadoop, which is kind of an ecosystem. It's a platform. It's a bit an operating system for big data, if you wish. Now the new version of Hadoop is called Yarn. So you can think of it, again, as an operating system. So it gives you tools to work for this big data, right? And it's kind of a synonymous today with big data. If you say big data, people will say Hadoop. If you say Hadoop, people will say big data. It's really the most successful kind of platform for big data analysis, processing, storage. It's used everywhere. You can see a map here for Google Trends. You can see that the trend is still going up. It's used everywhere, even in Switzerland. Most of our big Swiss companies right now, they have a Hadoop cluster. From trains to the government to banks, they are all trying actually this Hadoop technology. So we have 1 Hadoop project in my lab in partnership with VeriSign. It's actually Benoit, where is Benoit, who introduced this project to us, and it's actually a very nice, small problem which we gave to one of our master students from Bern. And it's about how to place the replica in this file system. So the Hadoop file system is extremely good because you can use it on many machines, right? The big novelties Hadoop is that you're not confined in terms of your database to 1 machine. You can use N machines, like hundreds, thousands of machines to store and process your data. How does it work? All your big files are chunked, and you have here the green rectangle. It's a chunk of data, and the chunk of data is stored on 1 machine in the cluster, and it's then replicated on 2 other machines. Why do you replicate this on 2 other machines? Because we're talking about cheap machines here. That's how you can scale out. That's how you can basically use thousands of those machines. Basically cheap machines which will fail, right? We say failure is the norm, meaning that machines fail all the time. If you have thousands of machines, you always have a few which will be down, right? So you have this safety mechanism where the data is replicated 3 times, which is awesome because you can basically, if 1 machine fails, you can still use the system. It's awesome also in terms of reading. You can read from different machines, but it's a huge also burden on the machine, right? You need to store everything 3 times. So what Benoit told us is that, hey, we have this issue that we have different machines in our data centers. We have small machines, old machines, we have big machines, which are much better. And Hadoop doesn't understand that. It doesn't understand that some machines are better than others. And there is also a problem in terms of the granularity. So basically what we built together with the master student is a new version of Hadoop, which is hardware aware, which means that if you have in your big cluster some machines which are faster, let's say they have a better disk, right? They have an SSD perhaps, then probably you should use that machine more to serve the data because it's faster. It's the same with the CPU. If you have some old machine with an old CPU and a new machine with 8 super fast CPUs, you should probably try to leverage this heterogeneity, right? So that's what we did, basically. We have this new algorithm to detect which machine is underutilized, to put more data on this machine, and then to serve more data from this machine quickly. It moves more block to the better machines, and it operates at the file level. So it's better in terms of what you can do in terms of the files. And like this, it's a bit magic, right? It's a slightly more complex algorithm, of course, without changing anything to the cluster. For some of the HDFS and Hadoop problems, we have a 3x performance improvement, right? Suddenly, we tripled the cluster without spending a dime on the machine themselves by better utilizing the different machines. So that's the volume example. I will be very quick and present you 2 further examples. We have a nice velocity example. Velocity is all about, again, those typically sensors which give you data. And we are working in this context in terms of smart cities. It's another kind of big trend in IT. It's how to leverage sensors in a city to optimize the city. And we worked in 2 domains in that context. We worked a bit on electricity provisioning, how to know what kind of electricity demand we will have, and on water networks. And it's been super, super fun because I have 0 knowledge in terms of civil engineering, and I never thought I would work on water distribution networks, and that's what I'm doing now. So the idea is as follows. In all big cities, you have those water pipes, right? Which usually they are old. And believe it or not, but they leak, they burst, they are contaminated, and roughly speaking, in any big city, 30% of the water disappears, right? Is lost, which is like, it's crazy to me, right? Like New York is losing 30% of its water. Same for many big cities. Why? Because it's difficult, right? Those networks are big, they are old. Sometimes it's easy to see if you have a leak, right, in your neighborhood. Sometimes it's much more difficult. And they have maintenance teams going a bit around, but not enough people, of course. They wait for someone to call them. It's very hard to dispatch the team. So we try to automate all of this. And we had a project also using stream technologies, so these velocity technologies using Storm, that's the name of the platform, to basically try to automate all of this in terms of try to detect those leaks. How does it work? The idea is to have sensors, right? This is a water distribution network underground. You have pipes, and you put those kind of cheap sensors at each crossroad in the network. And those little boxes, they give you some data continuously. They give you, for example, pressure data. Is the pressure high enough or not high enough in the pipe? They can give you speed data, quality of the water data, right? And we basically build some kind of Internet of Things, right, algorithm to share this data and to have some statistics on the data. So here is the result. On the upper left corner, you have a real network, right? Those are pipes, lots of pipes under a city. And you have kind of the real value of the pressure inside the pipes. You have different colors. The second graph on the right is what we get from the sensors. We install some sensors in those pipes, and we get this very noisy kind of picture, right? And we cannot say much from this noisy picture, but then we have our big data kind of pipeline. We apply statistics, and we basically try to understand if one particular pipe has a much higher or lower pressure compared to its neighbor, right? If everyone in the neighborhood has a small pressure, and one pipe has a high pressure, it's a very bad sign, and the other way around. It means that you have an anomaly. So we do our statistics. We get basically this picture here, and then we do some more advanced statistics to just get the outliers, and we get finally this, that's what we want, where you have a few points in the network, actually many, right? It's not surprising, I guess, but it's a bit scary. You have all those red points, which are very different in terms of pressures than the other ones. Again, those are the points where you want immediately to send someone because the pressure is much, much higher at those points than in the neighborhood. That was the velocity part. Finally, I will talk about variety, one of my favorite topics, because again, it's so complicated. We have decades of research in terms of variety, in terms of how to tackle those issues. So I will be very brief. I gave a full presentation in Reston for VeriSign about like 1 hour on this project. This is a project which was financed by VeriSign. So we won one of the 2 internet infrastructure grants, which were available globally. So we are very happy to have won this grant. Thanks a lot, VeriSign. And we built for them, so the idea of this grant was to build some system, open source kind of, to help a bit the usage of internet in poorly connected kind of countries, right? And this is a graph from one of our students who is from Tanzania. It's an interesting graph, right? Because you see on the y-axis the cost of your mobile data, and on the x-axis the cost per bundle. So what you see basically is for Switzerland here, the cost rapidly goes to 0. Because if you're like me, if you like a bit to surf online using your mobile phone, you have a flat rate, right? You can surf and be always connected. It's going to cost you basically only your bundle, like 60 francs, 100 francs per month. In Tanzania and in many developing countries, this is unfortunately not the case. You can see that the line goes flat, but it doesn't go to 0. It means that in Tanzania, every time you use your mobile phone to get on the web, you have to pay. What's the consequence? It means that those guys, they are not always online, right? And this is a huge problem today because many applications, they are data-driven, as I was trying to explain you, right? It means that you need to have access to the web to power the new applications, right? Think about all the new Google applications. If you're not connected, you can forget about Google Now or Google whatever. So we want to bring those applications to the developing countries, and we built this new system, ERS. It's a system where basically different devices, like this phone, even if it's not on the web, can exchange data, right? Can consolidate data. So we have like a local mode, and then a bridge mode, where in a neighborhood, in an ad hoc fashion, like machine to machine, you can exchange and integrate data. And once you have a data connection to the web, you can use the web and globally synchronize all your data, right? So it's kind of a database, if you wish, but for device to device, and where devices, even if they are not always connected to the big internet, they can create those islands of data and then transparently synchronize all the data. This is open source, and this is being deployed in the several countries. So we have 2 big partners. We have the Sugar Labs. You might remember those cute green laptops. They are the XO laptops, right, from the MIT Media Lab. So we have basically, now we are part of their distribution, and all the tens of thousands of laptops which are used in Asia, in Africa, now can use our system to communicate, right? So basically, students in a classroom, they can communicate between them. They can then have a bridge to bridge to a second classroom, and when they are connected to the internet, they can talk to the rest of the world. And we are also deploying this with VU University in Amsterdam for elderly persons, right, which also might be a bit isolated, but such that they can also communicate using those devices. That's all I wanted to say today. Big thanks to VeriSign, to the local team, Vincenzo, Benoit, Matt, Romain, Big thanks to Bert for his support and to the Internet Infrastructure Grant, which gave us this award. Thanks a lot. It's been a very fruitful collaboration. We are so happy to have you guys here in Fribourg. This is our website. We've published all those different projects in journals and conferences. So check it out if you want to have some more technical information. Thanks a lot to the XC crew, my students and postdocs. They are a bit around. Some of them are here. They did all the hard work, of course. And if you have questions, I'll be happy to answer them.
Thank you very much.
Thanks a lot.
Well, we've come to the conclusion of the event, and I'd just like to recognize a few of my colleagues who've made it possible. Our Distinguished Speaker Series Program Manager based in Reston, Angelique Feinan. We have our production experts here, Uti Dallenbach, Chris Curtis, and Clinton Marais, and our university team with Vincent Remy, Benoit Perrault, Vincenzo Russo. I thought I would not need my notes, but I apologize. Regis Picard and Nipun Jalwapaz. Thank you, both Philippe and Jean. It is late in the day, and I apologize for the jet lag, but thank you both for that. And then finally, thank you all for coming, spending your time with us, being our guest, and supporting the work we're doing here in Fribourg and in Switzerland. Thank you and enjoy.